All right, so here's the situation. My understanding is that the Algebra 2 Honors course for distance learning has skipped sequences and series entirely. Um, and so we're in Chapter 9 for pre-cal, and the second half of Chapter 9 is sequences and series. Um, but it kind of assumes that you've at least seen them before, and then kind of takes it a step further and kind of starts to introduce you to some of the calculus ideas that you would start to see with sequences in calculus. Um, but since apparently most of you guys have never seen sequences before, what we need to do is just kind of take a step back. We're just going to do the Algebra 2 sections for sequences. We're not even going to do the sections from our pre-cal book on sequences, which is fine. Really, you just need the basic understanding of what sequences are and how they work. Um, and then you can just do the calculus with sequences when you get to calculus, and you just won't get the kind of preview that we would normally give you. But you don't really need the preview of calculus. What you need is the basic understanding of what a sequence is and how they work. So for these last few sections of the course, we're actually going to go backward. You're going to finish pre-calculus by doing algebra 2, taking a step backwards. And so you'll see for your assignments, they're going to be out of the Algebra 2 Honors book. So there's going to be a new link for the textbook to be able to get into the Algebra 2 Honors book for the pages that you need. Um, so look for that. There'll be a different link for getting the answers to check. It won't be a full worked out solution manual. It'll just be the answers. So it'll be a little bit different for these last few sections, but we got to kind of fill in the gaps that happen with distance learning here. All right. So sequences. What is a sequence? A sequence is just a list of numbers. That's all it is. So I mean, you might have actually seen these before, even like in elementary school, probably looking at patterns. And patterns is going to be a big thing when we look at sequences here. So it's just a list of numbers, and we call each number in the list the term, a term. And so we got the first term, second term, third term, fourth term, and then they often go on forever. So we have this dot 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 here at the end. And the notation that we use for sequences, we pick a letter. Could be A, could be T, could be whatever letter we want. And then we use subscripts, these little small numbers. When you read a number kind of small and down to the right, this is called a subscript. We use these to number things. Like you've seen that in your, like in the slope formula where it says y2 minus y1, x2 minus x1. It's the second y minus the first y, second x minus the first x. These are just number things. So this is like the first A, the second A, the third A, the fourth A. This just means the first term for the A sequence, if we're calling this sequence A. So the subscript here, this means the first term. So A sub 1 is 3. That's how we read this here. We say A sub 2 to read a subscript. A sub 2. It's 5, so the second term is 5, the third term is 7, and the fourth term is 9. All right. So what if we want to find some more terms of the sequence? What if we want to, the dot 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 means this keeps going. What if we wanted to find some more? So again, one of the big things is going to be looking for patterns here. So hopefully you can see this is a pretty obvious pattern here. We're just doing plus 2, plus 2, plus 2. So then if we wanted to find the next term, we would add 2 again. And of course, that would be 11. And so and that's what A sub 5 is. A sub 5, that's the fifth term in the sequence. So that would be this 11 here, this next term that we just found. So A sub 5 would be 11. Well, then if we wanted to find A sub 6, that would be the next one. We could just add 2 again. The next term after that would be 13. This, again, would just keep going here. So A sub 6 would be 13. So then A sub 10, that means the 10th term. That means the 10th number in the list. So if we wanted to just kind of keep going, I mean, we could keep adding 2 till we got to the 10th term. But let's try to be efficient here. So how many steps do I have to go from the 6th to the 10th term? Well, that would be 4 steps, right? So from this one to the 10th term, I have to do 4 steps of 2. I need 4 2s. I'm going to add 2 4 times. So I'm going to add 8. So the 10th term would be 21. What if I want to jump all the way to the 100th term? Well, from the 10th term to the 100th term, how many steps is that? That's 90 steps forward, right? That's 90 times that I would have to add 2. So I would have to add 2 90 times. All right, so I'd have to add 180, so that would be 201. Now, another way, though, that you could have figured out these numbers here without, of course, just doing plus 2, plus 2, plus 2 until you got that number in the list is what if you could figure out the formula, the pattern for, well, when I have the third term, is there something that I can do to 3 to get 7? Is there something that I can do to 4 to get 9? And so then what can I do to 100 to get 201? What can I do to 10 to get 21? To try to figure out the pattern that way. Well, kind of one clue here is we're adding 2 repeatedly. Repeated addition, that's what multiplication is, right? This right here, plus 2, plus 2, plus 2, plus 2, plus 2, adding 2 5 times, that's 2 times 5. Repeated addition is multiplication. And so if we're adding 2 over and over again, what we're going to have is we're going to have some sort of multiplication by 2. We're going to have 2n in there. We're going to have 2 multiplied by something. Okay, well, let's check. when it was 100, so 2 times 100 would be 200, but we had 201, so we're off by 1. If I do 2 times 10, that would be 20, so we're off by 1. Take a look at this. All of these, it's just one more, right? 2 times 4 plus 1, 2 times 3 plus 1. So the formula would be 2n plus 1. All right. So what we call that the explicit sequence formula. A sub n is 2 plus 1. That's the explicit formula for this sequence because it explicitly, it directly, it in a straightforward way, allows us to find what the term is for any number term. So like take a look, instead of doing this stuff right here to find a sub 100, I could have just plugged in 100. I could have done 2 times 100 plus 1. That would have given me 201. Down here, if I want a sub 73, if I want the 73rd number in the list, instead of just doing, plus 2, plus 2, plus 2, plus 2, plus 2, listing out like, 73 numbers, instead of doing that, I can just use this formula. I can say 2 times 73 plus 1. Let's see, that's 14 and a 6, 146 plus 1, so that's 147. Same thing if I want the 95th term. Any number term, whatever number term in the list I want, I just take that number and I plug it into this formula here. So 2 times 95 plus 1. Let's say it's 180 plus 10, 190, and then the 1, 191. Okay? So this explicit formula is kind of like a function. Okay? So it would be kind of like we have the function 2x plus 1. So we're used to functions where we have x as an input and then f of x or y as an output. So for the sequence, it's kind of like the number term is the input, and then the number in the list is the output. So we would say if we input 1, if we say we want the first term, then the output right here, the number in the list, the first term is 3. Right? So you can look at this sequence right here. Like we input 1 and we output 3. We input 2, we output 5. We input 3, we output 7. Input 4, output 9. Okay? The place in the list that we are, the number term we're looking for is the input, would be kind of like the x. And then what the number is would be the output, kind of like the y here. Okay? The only difference between sequences and functions are with sequences, we're just talking about a first number, a second number, a third number, a fourth number, a fifth number. We can only use whole numbers for our inputs. Okay? There's no -1 term. And we usually start with talking about the first term. You'll see in the next couple of days the fact that we start with our first input being 1 instead of 0 is going to make things a little bit messy sometimes. we start with 1, 2, 3, 4, 5 for our inputs. With a function, you could have x be anything you want, right? So if I'm looking at this just as a function, I could say let's make x be -1, and I could plug in -1 into this function. -2 plus 1, I could say y is -1. I could change this 2 to a 2.1, plug in 2.1 into that function. 4.2 plus 1, this would be 5.2. For a function, no problem. For a sequence, I can't make this be -1 right here. That doesn't make n can't be -1. N has to be a whole number, one or bigger. I can't make this be 2.1. You can't have a 2.1th term. Right? All I can do is I can just keep going forward. I could add 5 into the list here. The fifth term was 11. If I plug in 5 to the formula, 2 times 5 plus 1, I get 11 for the fifth term. But that's all I can have for my inputs. Okay, so these sequences and functions are kind of very similar, just with particular inputs. Okay, so why don't you go ahead and give this a try now? Let's say I give you an explicit formula here. Again, this is just kind of like a function, where instead of x we've got n, and instead of f of x we've got t sub n, and you can't plug in any numbers you want to it. You can only plug in the numbers 1, 2, 3, 4, 5, 6, 7, and so on, those kind of whole numbers. Okay, so given this explicit formula, kind of like a function, why don't you go ahead and take a minute and just write out the first 4 terms of the sequence for me. All right, and then also take a look at this down here, see if you can make heads or tails of this. We've got a couple special types of sequences. So the 3, 5, 7, 9 we just looked at is called an arithmetic sequence. I know it looks like arithmetic. It looks like arithmetic, but it's actually pronounced arithmetic. So that was called an arithmetic sequence. Then there's also going to be geometric sequences. So these sequences have particular kinds of patterns, with either a common difference or a common ratio. Take a look at that, see if that makes sense to you, and see if you have any ideas. Take a guess for the 3, 5, 7, 9 that we were just doing. Take a guess what the common difference, what the D might be. And then for this sequence right here, just take a guess, see if you have any ideas. Just take a wild guess what the common ratio with the R might be. So take a look at these last few things on the page, and you go ahead and give those a try. Right. So not coincidentally at all, the first 4 terms of this sequence in this example were the ones that I had here for our geometric sequence example. So this sequence T sub n here is the list of numbers: -2, -6, -18, -54, and so on. That's an example of a geometric sequence. Okay, so arithmetic sequences are going to be the ones where the pattern that you see is adding or subtracting numbers. Okay, so if the pattern looks like it's adding or subtracting numbers, then that's going to be an arithmetic sequence. And the kind of funny thing is we call it a common difference. Difference means subtraction, right? You look at this and you see adding. So when you see the pattern is +2, the common difference is going to be that 2 right there. What we look at is the difference if we subtract it backwards. So if I do 9 minus 7, or if I do 7 minus 5, if I do 5 minus 3, if I do any one of those subtractions, common means that they all have the same thing. So they all have the same difference. The subtraction for all of those would be the same thing. It would be 2. Okay. For geometric is going to look like you're multiplying by a number over and over again. Okay. We look at this and we see the pattern is times 3 times 3 times 3. Okay. Notice we had something exponential in the formula. So repeated multiplication turns into an exponent. When we had repeated addition turns into multiplication in the formula. That's going to be important in the next couple of days. Repeated addition turns into multiplication. Repeated multiplication turns into an exponent. Okay, so geometric looks like multiplying over and over again, but we call it a common ratio. Ratio is a fraction, is division. right? So this way, again, if you divide it backwards, so just like common difference, we subtract backwards, the common ratio, if we divide backwards, if you divide any consecutive pair of terms, so if you divide -54 divided by -18, -18 divided by -6, or -6 divided by -2, they all have that in common. They all have that same ratio. Those all would be +3 there, and so that's the r equals 3. Okay, so we're going to talk more about arithmetic and geometric in the next couple sections. The next section we'll talk about arithmetic, and the one after that we'll talk about geometric more. Right now, we're just going to ask you to identify whether things are arithmetic, geometric, or neither. Okay, and we'll start by just making sure that we see the pattern by having us fill in the next term here. So take a look at 5, 9, 13, 17, see what that pattern is. That pattern is +4, right? +4, +4, and +4. So then to find this next one, we would add 4 again, and we would get 21. And so if we're adding over and over again, which one is that, arithmetic or geometric? That one is arithmetic. Okay. And again, for arithmetic, it could be subtracting as well, right? Like, because we could add -4. Subtracting is the same thing as adding a negative, right? So if this sequence were flip-flopped, if it started at 21 and then went down to 17, 13, 9, 5, that would still be arithmetic, whether you're adding going up or subtracting going down. All right, take a look at this one here. Okay, so here I add 9, then I add 11, then I add 13. So it can't be arithmetic. It doesn't have a common difference. I'm adding different numbers. Okay. Geometric would be kind of a funny fraction to multiply every time. I mean, I could try finding 49 divided by 36, compare it to 36 divided by 25, check if those ratios, check if those fractions are the same. You could check that, but it's not. This one has a different pattern. This one's actually neither. This one you're not adding or multiplying by the same number every time. It has a different pattern. Can you tell the pattern? Do those numbers look special to you at all? 16, 25, 36, 49. Those are special kinds of numbers. Those are perfect squares, right? 16 is 4 squared. 25 is 5 squared. 36 is 6 squared. 49 is 7 squared. So the next number in the list would be 8 squared, would be 64. Often, if it's not arithmetic or geometric, it probably has something to do with perfect squares. That's the other common pattern that we'll see. All right, let's try to take a look at these numbers here, see if we can see what the pattern is here. 64 to 16 to 4 to 1. The pattern is dividing by 4. If I divide by 4 each time, that works. So then the last one here, if I divide by 4 again, 1 divided by 4, that's 1/4. Okay. So what do you think about this one? Is that arithmetic or geometric? That one's going to be geometric. Dividing by 4 is the same thing as multiplying by a fourth. So again, arithmetic is going to be adding or subtracting. Geometric is going to be multiplying or dividing. And so when we have this right here, again, we'll talk about this more in a couple sections, but for something like this, your r would be the 1/4. R is what you're multiplying by every time, or if you divide it backwards, 1 divided by 4 gives you your r. All right, so that's sequences. We'll talk about that more coming up in the next couple of days. Next couple sections. So sequences were just a list of numbers. They're just kind of sitting there, kind of like a function, kind of like a table of values. Series is when we take those numbers and we do something with them. We add them all up. Okay, and we have a notation that we often use for that. It's called sigma notation. So this right here, this symbol is the Greek letter sigma. It's the Greek letter S. I know it kind of looks like an E. It kind of looks like a big E. Some people even call it the big E, but it's not. It's actually a big S. It's the Greek letter S, the Greek letter sigma, and so we use that for sum. It's a Greek letter S for sum. And so sigma means sum. So it's going to show us a formula. So what's on the right side here is going to be the formula, is going to be the explicit formula, kind of like the function. Okay? So like when we had this right here, that explicit formula, or this explicit formula here, a formula like that, that's going to be this thing on the right side here. Okay? That's the formula. And it's going to tell you where to start and where to stop in the sequence. Okay? So this one starts with the first term, but you don't always start with the first term anymore. Sometimes you might only want to add, starting with the second term. You might not want to add in the first term. So you can start with this one. You can start anywhere you want. With sequences, when we have a list of numbers, well, the first one is the first one. If it's just a list of numbers, we always start with the first term. With sigma notation, we're going to be able to start wherever we want. We can start with the second one, we can start with a third one, whatever we want. Right? And then this number on top is going to be the last number term. Okay? It doesn't tell us how many things we're adding up. It doesn't tell us how many terms. It's going to be the last one. It's going to be where we stop. Okay? So let me show you how this works here. All right. So what this means, so this is the formula, and we want to, for this sequence, what we want to do is we want to add up the second term, the third term, the fourth term, and then we're going to stop at the fifth term. Okay. So we're going to take k equals 2. And we're going to plug it into the formula. We're going to figure out what the second term is for this sequence, for this formula, for this function. So plug it in. So we'll have -1 squared, and then 2 times 2 plus 1. And then that's our second term, right? Whatever number that is. That's our second term, right? So we can figure it out, right? -1 squared, that's just +1. 2 times 2 is 4, plus 1, so that's 5. Okay, so for this sequence, the second term, the second number in the list would be 5. All right, but for this problem, that's the first one we want to start with. All right, so then we'll take a look at k equals 3. So we'll plug in 3 to this. -1 cubed times 2 times 3 plus 1. So -1 cubed, negative, 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 3 negatives is negative. So I'm going to have negative, and then 6 plus 1, 7. Right? So for this sequence, for that list of numbers, that's the third number in the list. Right? And that's the next one we wanted here. Okay, so then we're just going to keep going. So we started with k equals 2, and we just keep going up by 1. So we did k equals 2. Now we did 3. Now we're going to do 4. Plug in 4 into this formula. -1 to the 4th. 2 times 4 plus 1. 4 negatives turns positive. And so 2 times 4 is 8 plus 1. So we've got 9. Okay, so that's the next number in the list. Okay, then we keep going. 2, 3, 4. Then we go to 5. Okay. So -1 to the 5th. 2 times 5 plus 1. 5 negatives is negative. 10 plus 1, 11. Right? Now here's the question. Do we stop there, or do we need one more? And the answer is we stop here. Okay, so this tells us where to stop. That's the value of k to stop at. That's the last one that you plug in, the last value of n, or here the last value of k. Notice we can use all kinds of different letters for these things, doesn't it? It's not like functions where x and y are, kind of the always ones that you use. For sequences series, we got lots of different letters we can use. Okay, so this is the value of k we stop at. It's the last number that we plug in, so it's not the number of terms. Notice we only have 1, 2, 3, 4 terms because we started with the second one and ended with the fifth one. All right, now this says compute though. So I wrote out some numbers. Compute, what do I do with those numbers? Well, remember sigma means sum. It means that we're adding together these numbers. So we have to add them. -2, +7, -4. Sigma means sum. Okay. All right, so I'm going to have you try that other one in just a minute here. But first, why don't we try to go backwards? What if I give you the series? What if I give you the list of numbers added together? And I want you to go back and write this formula right here. Let's try to go backwards. Okay, so I'm going to write our sigma here. Okay, and then pick a letter. I'll just use N. Okay, first let's see if we can see what the pattern is. Okay, well it's going up by fives. I mean, this 5 times 1, 5 times 2, 5 times 3. Looks like it's just multiples of 5. Looks like it's just 5 times a number, right? So 5 times a number, 5n. All right, well, what's the first one right here? That's just 5 times 1, so the first thing we want here is just 1. Okay? So this number here, when I plug it in, has to give me that first number right there. Well, what about this number? This number, when I plug in this number, it has to give me 250. All right? So whatever number this is, I have to get 250. So I need 5 to figure out this number. I need 5 times something gives me 250. Well, what is that? That's 50. So from 1 to 50. All right, and then that's our answer. That's it. That's all we need. Okay. Now, if you have a little bit of trouble figuring out this formula right now, don't worry about it too much. Part of what we do in the next couple sections is talk about how do we find these formulas, some rules, some formulas to find the formulas. So if you have trouble in this first section with it, don't worry about it too much. We'll give you some help in the next couple sections. Just do your best. Try to look for the patterns. Again, here the pattern was plus 5, plus 5, plus 5. Repeated addition turns into multiplication. Repeated multiplication would turn into an exponent. Okay. So why don't you go ahead and see what you can do with these last couple problems here. So in this one, you're going to write it out. Again, start with the bottom number, plug it in, and then just keep going up by 1 and just stop at the top number, plugging it in to those into that formula right there. And then this one might be a little bit trickier. See how you can do with this one right here. See if you can go backwards on the second one here. See if you can figure out how to write the formula for it. Might be a little bit trickier, but give it a try. Okay, so go ahead and do these last two problems here. Right, and here are the answers here. So this one should have been 10 plus 11 plus 12 plus 13 plus 14, should have given you 60. So again, we had to start with, you don't have to write this, by the way. I don't need to see this in your work. This is just to show everybody how it works. But we started at 3, plugged in 3, plugged in 4, plugged in 5, plugged in 6, and then the 7 tells us to stop at plugging in 7. Again, we only have 5 numbers. This doesn't tell us, we don't have 7 numbers. We only have 5 numbers. This tells us to stop at plugging in 7. And then remember to actually add them up. Sigma means sum. So we have to actually add up those numbers. And then for this one down here, there's a whole bunch of different possible answers here. Okay? So the pattern in the denominators was plus 2, plus 2, plus 2, plus 2. So adding 2 over and over again turns into multiplication. So we had to have some sort of 2n. And then we have to kind of tweak a little bit. And depends where you're starting. So again, sequences, it's going to be a little messy in the next couple sections because we always have to start with 1. But with sigma, you could start at 0. You could have looked at this like it was a linear pattern. You could have said the slope was 2, the constant rate of change was 2, the starting point was like the y-intercept. You could have thought about that like mx plus b if you're starting at 0. All right. If you start at 1, then you just have to figure out, okay, what do I have to do to make this work? If this is the first term, then I'm only at 2, so I have to add 3 to get 5. And then the second term, I'd be at 4. I have to add 3 to get 7. Third term, 6 plus 3 gives me 9. Or if you were comparing it to the sequence that we had at the beginning, the formula was 2n plus 1, and we just started at the second term. It was almost the same as the sequence we had back here, right? We just lopped off that first term. So you could have said, well, let's just use this formula and start at the second term. Okay? Either way, there's going to be lots of different answers. Okay, so it's possible when you're checking answers that your answer is not there and you still got it right. All you have to do is just plug in a few numbers. Don't just plug in one, but plug in two or three numbers and see if your formula actually works, if it actually matches. Okay, and again, to find the number at the top, you can just set your formula equal to the last term and solve for it.